Hello everyone. So, in the previous video, we talked about the series pass voltage regulator. We did a very thorough overview of the theory of how they work, and we went through from a simple buffered zener to a very simple discrete adjustable voltage regulator like this. And in the end, we finalized it with the classic circuit, the very crude one of a voltage regulator based on an opamp. Okay, so after all that theory, in today's episode, I decide to go one step further, and we are just going to look at a very simple, let's call it the basis of any sort of lab power supply. Okay, so first things first, any lab power supply must have two things: voltage control, so the voltage should be adjustable, but also it should have current control, because you gotta be able to limit the current, not just trip the output if the current exceeds a certain level or something like that. No, you need to actually be able to control the current. This is very simple and can be implemented in a number of ways, but it is key to any sort of lab power supply. Because hey, let's say it's in a lab environment, you don't know what you're going to be powering up with it, so it has to be as versatile as possible. So if you have a current controlled supply, you can use it to do current limiting, since you're going to be testing stuff that you're not sure if it's shorted, if it will draw excessive current and damage something or something like that. So you need to be able to do that, and sometimes all you need is just a current source. And if you limit the current, that's basically a current source if you want to power an LED or an LED driver or something like that. So that's pretty important on that setting. You also need a lot of protection, because hey, again, it's the lab environment. You have no clue what your end user or even yourself will be plugging into the output of that. So it has to be protected against basically everything you can throw at it. Current and voltage being input into the outputs, massive overcurrents, transients, inductive loads, capacitive loads. It has to basically just handle all those circumstances as best as possible. But in this episode, we are just going to look at bare bones. In the circuit that I'm going to show you here, it's very generic. It's going to be kind of like the basis for the high voltage power supply that we'll be building here in this channel. But it's so generic that you can use it for everything. If you want to build, for example, a 30 volts, a 0 to 30 volt supply, whatever you need, that circuit's going to be your basis for that. All you need to do is just adjust some of the values of the components, change the current sense resistor or the pass elements, either for more current or for more voltage. That's all up to you. But it's going to be a very versatile circuit and something that you definitely should build yourself. Okay, you don't need to buy a fancy power supply for your lab. You can build it on your own. It's very simple. It's a great project. You'll learn a lot from it, and yeah, and it's very rewarding. Okay, so let's jump right into that. So first, let's talk about the voltage control, just as we've seen here. Okay, so I've done this in a LT Spice, just to make things a bit simpler and easier on me. So that's why it's using the American notation. Okay, that's not something that I like, but it's the way it is. I didn't want to go to Eagle and redraw this whole thing, since I already had it on LT Spice. So let's talk about this circuit, okay? First of all, this circuit, it's basically the same thing that we had here, just with some modifications. Of course, it has a lot more supporting components around it. That's because of the whole current control part of the supply. So you can just ignore this sense resistor, you can ignore this capacitor and resistor here, and stuff like that. Most of this, it's just for frequency compensation and mitigations in terms of oscillation of the circuit. Again, hey, you have no clue what's going to be attached here, so you need to take care of all that. That's why most of the times beginners, when they design a circuit like this, you don't see any resistors. It's just everything's just connected together and stuff like that. And then they just look at a professional circuit and they have no clue why there are just so many resistors, so many capacitors. Hey, that's all about compensation and making sure that your circuit is stable and precise. Okay, so we're going to be going through some of that here in this video in a little bit, as soon as we complete the circuit with the current control part. But for now, just ignore all this fluff, okay? So we still have the same topology with the pass element. This is just a resistor to make sure that this transistor here in the Darlington pair shuts off faster than normal, okay? You can learn more about why this resistor is here in my Darlington and compound feedback pair video, which I'll probably throw up a card right here. Now we have this current sensing resistor here. Let's not worry about that right now. We have a little bit of capacitance here in the output just to smooth out any transients. Whenever you have a lab power supply like this, don't put a lot of capacitance in your output. I know you're just used to just throwing capacitance at the problem. Hey, if you have any ripple, if you have any noise, just throw capacitance at it. That's not how it should be done, especially on a power supply, in a lab power supply like this. Because the bigger you make this capacitor right here, the more problems you're going to have. Because hey, let's say that your load that's right here, let's say you put a 1000 microfarad capacitor here, just so that you're 100% sure this thing is going to withstand any sort of transient, just going to curb all that noise. There will be a huge problem, because let's say you're plugging in your circuit here, and all of a sudden you make some bonehead mistake, and you short the supply. Okay, you have a MOSFET that was supposed to be controlling an LED or motor or anything like that, and something goes wrong and it just shorts the supply. That capacitor is just going to discharge onto your circuit, and it's just going to destroy whatever transistor that tried to short the supply. So that's not good. Okay, so this capacitor here, it's basically there mostly for noise suppression and a very small transient mitigation. Okay, so put as little capacitance here as possible. Now, this resistor here, it's just again for frequency compensation, just to keep this whole thing happy. Same thing with this capacitor here. This just provides a low impedance path, feedback path for high frequencies, just in case, hey, this opamp starts to oscillate. It will oscillate, especially as soon as we attach the current control here. This thing would oscillate like crazy whenever you hit the current limiting. Okay, so you need this so that high frequencies just have basically just a short to the feedback node, so that it doesn't amplify any sort of oscillation and just makes this circuit operate properly and be stable. Same thing here. So as soon as you look at this, the first thing that you need to keep in mind is that before here, what we had was we had a reference here come to the non-inverting input, and we were basically just amplifying this reference with this feedback network here. In this case, it's a bit different. We're amplifying our set voltage, or our reference, okay, by a factor of 10, because hey, that's the classic non-inverting op-amp formula of gain. It's just the ratio between these two resistors plus 1. So in this case, it's going to be 10 times gain. And instead of having a reference, what we have here is just a voltage input. Of course, this voltage input should come from a reference. So just like we had here, what we could have here is just this layout like this and just put a potentiometer here and the output of the potentiometer coming to here, and it's going to be basically the same thing. The idea here is that on a circuit like this, these resistors are the ones that are setting your output voltage, okay? But if you make it into this configuration, you can't control this, for example, from a microcontroller, because you will need to be varying this network right here, so that's no good. And this way, it's extremely versatile. So you can just put the output of a microcontroller here, and you can control the voltage here in the output. All that it is doing is amplifying whatever voltage that you put here by a factor of 10. So if you put 1 volt here, you have 10 volts here on the output. It's just as simple as that. Okay? So remember that this voltage here will determine the voltage regulation here in the output. So make sure that this is as noise-free, as ripple-free as possible, okay? Treat this as a variable voltage reference, okay? So make sure any sort of noise or ripple or any sort of undesirable side effects, this is completely free of that, okay? That's very important. So yeah, the voltage part is extremely simple. As you can see, this is basically just a voltage amplifier, a times 10 voltage amplifier. Okay, so with all that said, let's go into the actual current control part of this, because as it is right now, there is just nothing stopping you from drawing whatever load you want in here, okay? Just one more thing before we go into that. We have V plus here. Let's just assume whatever voltage you want here. If you want to put, let's say you want to go from, something that I didn't talk in the intro section. Another thing that a lab power supply should have, it should have the ability to go down to 0 volts, okay? Because hey, let's say sometimes you need 0.1 volts at the output with a lot of current. I've done that a lot when I just needed to test resistive elements and stuff like that, and all that I needed was 0.1 of a volt, and the resistor was pulling like 5 amps. Okay, so that's also very important. And now with a circuit like this, you can do that very simply. Something that you can't do, for example, something like an LM317. Okay. So let's say you want a 0 to 30 volt power supply. You don't put 30 volts here at V plus. You should put a lot more. Let's say if it was a as a classic like 30 volt 3 amp lab power supply, output here 40 or 35 on regulator here, and you'd be good to go. Okay, so just whatever voltage that you need here in the output, okay, just put some margin here in your supply rail. Okay, in this design I'm not going to be using a negative supply here for the op-amps, especially in the current side, but that's something that you could look into if you want to use some lower end type of devices. Okay, now let's take a look at this circuit right here. As the circuit stands, this is just basically a very simple, very crude lab power supply. Okay, this is the bare minimum that you should have in order to have any sort of power supply in your bench. Okay, so you can replicate the circuit and you can use it for your own supply, but hey, it's not the best circuit. It's not properly done. And we'll be taking a look at how to improve this and make it better in the next few videos, where I'm just going to talk about protection and all that. But hey, this is good enough, okay? So, first thing, as soon as you see something like this, it looks a bit daunting, as we've discussed previously on the headphone amplifier series and the shunt regulator. Hey, as soon as you get a circuit like this, it looks very daunting. You need to separate it into some very common building blocks, because every circuit is just a collection of building blocks most of the time. Okay, so first things first, you can see here that basically if you draw a line around here, This bottom part is just the current control, and the top part is your voltage control. Now, here on the top, as we've seen previously, this is just basically a voltage follower. It's just amplifying whatever voltage we have here. Here on this output, and we have a bit of a current buffering to increase our current handling capabilities. So this op-amp here is just amplifying whatever voltage here. Then it goes through a Darlington pair here to the output. So that's just textbook stuff. Now here on the bottom side, we have very low value resistors, so we know that the voltage here is going to be very low. So we are just amplifying that voltage again by a factor of 10. Okay. And here is the actual current control part of things. And if you see here, it's the same thing as here. This is just a voltage amplifier, a DC voltage amplifier. Very simple stuff, textbook stuff. And here, what you have, if you just look at the op-amp like this, you can see that there is no feedback, no negative feedback. In this case, it has, but again, this is just for preventing this thing from going into oscillation and controlling all of the frequency poles, making sure that this thing has good transient performance. Again, stuff that we're going to be talking about in a later video. And oh, by the way, this circuit right here, I will provide the LT Spice file so that you can simulate this on your own and play around with this. It's very important that you play around with this stuff in a simulator, just so that you understand, hey, just remove these capacitors one by one, just see how it works, increase this capacitance, decrease this capacitance, just see how the circuit operates and how it reacts to over voltages, over currents, and all sorts of scenarios. Okay, you're going to learn a lot by doing that, and I highly suggest you to do so. That's why I'm making this available for you. Okay. So what more can I talk about in here? So yeah, oh yeah, this thing is, it's hooked up as a comparator, and a very fast one, by the way. So yeah, that's that. What else can I say about this? Oh, by the way, these op-amps here, I just chose a very common op-amp on LT Spice just so that I could simulate this. These op-amps are not the op-amps that you should be using on your final circuit. Okay, just for this op-amp, choose something that has a very low input offset. Okay, the best that you can get, but there is no harm in just putting an LM324 here. Okay, same thing here. You can put an LM324, perfectly fine, or even better, hey, you can just put a very good comparator here. You could just put a comparator instead of an op-amp, no problems whatsoever there. Now for this op-amp right here, in theory, the best thing to do would be to actually put a very good op-amp here with extremely low voltage input offset. Okay, because this thing is going to be measuring very low voltages, so that's adamant for good current measurements. And ideally, what you should use here is instrumentation amplifier, so that you can actually measure this thing differentially and then put it into an amplification stage like this. Okay, so just some things to keep in mind. If you're doing something like this just for your bench, hey, you shouldn't just be using a instrumentation amplifier. Just put in an LM324 here. Slap in a negative supply, just a -5 volts supply, just so that you don't run into any sort of trouble with the input offsets and stuff like that. Okay, so that would be perfectly acceptable for the hobbyist at home. Okay, but if you're building something that has to have any sort of precision, you just go for an instrumentation amplifier with some gain. Okay, so what can we say here? First of all, you need to choose a sense resistor that will provide you with enough voltage here that you can amplify and have something meaningful here. In this case, I just chose a 0.1 ohm resistor. Keep in mind that the more current that this draws, the more voltage will appear across this resistor, making your differential voltage here, or the voltage that's actually going into your load, lower by a bit. Okay, so let's say if your load was drawing 1 amp, you would see 0.1 volts here. So if this was at 12 volts, your load would actually be seeing 19.9 volts across it. Okay, because this node is not referenced to ground, it's referenced to this point right here. And the more current you draw, the greater voltage appears across this resistor, and less voltage goes through your load. This can be mitigated. You could have put it here between the output of the passive element and your V plus in your the positive terminal of your load, and just tie this directly to your ground. But then you'd have to do high side current sensing, and if you're interested in that sort of stuff, I can cover it in a later video. Just leave your suggestion in the comments, okay? But the problem with high side is that you for sure you will need differential measurement there, which means you will need an instrumentation amplifier at least there to measure that, and things just get a bit more difficult there. This is supposed to be a simple circuit that anyone can build, okay? And so no instrumentation amplifiers, no fancy stuff. But this has that downside with a low side current sensing, that you get voltage differences here depending on your load. So you need to make sure that this resistor is as low as you can get in order to mitigate that problem. But you can't make this way too low, because then your op-amp might not be able to amplify that voltage. Another thing that you need to keep in mind is that the lower the voltage here, the more noise you have. So the more noise you have here in the output. So there are always trade-offs with any circuit that you build, okay? So you just have to strike a balance there, all right? So if this circuit was drawing, if your load was drawing 1 amp, you would have 0.1 volts here. So we amplify that by 10. You would have 1 volt here at the monitor output, just so that it's something that's more manageable. And this volt output here, this is just the monitoring voltage, so that you can, let's say, run this to your microcontroller or some sort of a panel meter or anything like that. So you can monitor your current right here. It's going to be amplified and low impedance, so that you can be sure to hook that up to anything that you might want. And that feeds into this comparator right here. And the way that this works is that you set your current limit by applying a voltage here to the inverting input of this comparator. So let's say I want to limit this the load current here to 1 amp. I put 1 volt here at this node. So what this comparator is going to do, the way that it's hooked up, whenever this voltage here goes above this voltage that's set here, so if there is 1 volt here, if this goes to, let's say, 1.1 volts, the output of this comparator is going to go high. And as soon as it goes high, what happens is it's going to turn on this transistor here, which is going to shunt the voltage that you have set right here. And when you do that, then this voltage here falls. And when this voltage here falls, you're basically just trying to find an equilibrium where this will be limited to that 1 amp by varying that voltage, okay? So this circuit, it's completely off, at least this. So yeah, there's a helicopter passing around here. No clue why. It's 8:30 at night. Okay, it's probably a military helicopter, because we have a military airstrip near here. Okay, so back to this. So basically, the way that this thing works is that it is shunting that voltage to find an equilibrium in order to keep this the current passing through here less than what you've set in here. One thing that you got to keep in mind as well is that this circuit, at least this part of the circuit, is completely off if you're in constant voltage mode. If you haven't exceeded your current limit, then this part is just off and it's doing nothing. It only kicks in when you need to, when it needs to. Okay. Now, in order for us to better understand this, let's just exemplify this. Okay. So let's just ignore your supply rate here. Just make it as high as possible for this example. Let's say we put 1 volt here and the VSET node. What happens is this op-amp is going to make sure that there is 10 volts here in the output and you have no load connected. Okay, so 10 volts will appear here. This circuit is going to be turned off. This is just basically going to be measuring the noise floor of the of your supply. Okay, so if we put a 9 ohm resistor here in the output, what happens is this load is going to try to pull around 1.1 amps through here, and let's say we have set this current limit to 1 amp by putting 1 volt here at the iSet node. So what's going to happen is as soon as you plug in that load, current will start to flow through it. The voltage here at this node is going to rise above that 0.1 volt. It's going to reach, let's say, 0.11 volt. 1.1 volts are going to appear in here. So there will be an imbalance here between the inputs of this comparator. So that it's going to turn on. By shunting this here, it's going to shunt this resistor to ground. And by doing that, it will lower the node here, which will lower the voltage here in the output. Again, this is just basically going to turn this on completely. But what happens is, since all of this is just linear, it's with all of these capacitors that we've added, this thing is not going to just shunt it completely. It's actually going to be putting a voltage here on the output, a current, because this is a common emitter type of topology. So basically, it's just going to put enough current here to keep this voltage at bay. And what voltage is going to be that? It's going to reach an equilibrium as soon as the load here is at 9 volts. So it's going to shunt some current here to make sure that this is a voltage divider and that 0.9 volts appear here in the input. That's just basically reaching that equilibrium. And as soon as we remove that resistor from here, this is just going to see that this node is lower than this node right here, so it's going to turn off its output, which is going to turn off this transistor right here, which will let this voltage rise to whatever value it needs, as it was before at 1 volt. So our 10 volts is restored in here. So it's pretty simple. You can see how this circuit is. It's pretty simple to understand as soon as we exemplify it. All right. Now, as you can see, if this thing just turns this on hard, this is just going to go to ground, and this load is just going to be turned off, which is a big problem. That's how we get oscillations when the current limit hits, because this thing is just going to be basically just pulsive modulating its output to try to maintain that equilibrium. And it's just going to be a mess. That's why we put these capacitors in here, just so that all that high frequency comes back to the feedback through the feedback path, and that's all mitigated and stabilizes the circuit. Okay. Also, if we have large transients here, same thing. These things are going to make sure that it doesn't overshoot or undershoot as badly, and also most importantly that they don't ring. If you put this into the an LT Spice and run simulations on this and change these values here, you'll pretty soon see how that's important and how it changes the output. Okay, it's very interesting and fun to do that. Let's see. Oh, another thing that these capacitors here, compensation, help. Let's say you have a dynamic load, for example, an amplifier. Okay, its current, the current that's going to be drawing, it's like a, let's say, a sinusoidal wave. And the thing about that is that, let's say that you have your current limit set to 1 amp, and it's just, and the amplifier is just going to be drawing that at a peak of the sine wave. What happens is, as soon as it hits that, this circuit will turn on, but then the load is going to lower as soon as the voltage lowers as well, because it's not caring about this voltage, it's just pulling less current. And what happens is that this circuit would enter into a state of oscillation just because of that, because this would then turn off, but this would then put your voltage lower, but then it would rise, and then this would turn on again, and it would just create some feedback that would create those oscillations. So that's how that stuff happens. Okay, so yeah, this was it. This was pretty simple. I don't think I can talk more about this. You're probably just bored to death with this, but hey, I hope you've enjoyed it. Okay, so this is a very good circuit. You can just take this as it is, put this thing onto some perf board, put some nice heat sinking onto your pass element, just this element, right, this transistor right here, because hey, this is the only one that you want to cool off. You don't want this to be getting hot, since its VBE changes. Okay, so just put this on a nice bit of heat sink, get a transformer, create an unregulated supply, which you can check out my video on how to properly design an unregulated supply. Put it right there. Hey, put some banana post on the front. Get one of those eBay voltage in the current meters, and hey, you're all set. You have your lab power supply. So this is very versatile. You can just put an Arduino here and set your voltage and currents. The sky is the limit with this sort of stuff. But this, I hope that you use this on your next project. It's very versatile. And again, a great circuit to have on your circuit toolbox. All right. So in the next video, what I'm going to be talking about is more about the safety aspects of this, and actually making it safer for use on the bench with stuff like, hey, if you have a capacitance in the output here, that your load has capacitance, not the actual capacitance inside of your lab supply, how to deal with that. So you're going to talk about crowbars and protection diodes in the output, and the inputs and outputs of a circuit like this. We're going to talk about hard current limits for overload of this supply right here, and all of that sort of good stuff. Okay, so be sure to check out the next video where we actually ruggedize this circuit for general lab use. But as it is, it's pretty okay. I'll just put a diode here at the output, just so that there is some mitigation against capacitive and inductive loads. But hey, just watch that next video and decide what you want and what you don't want to put in a circuit like this. Okay, so I'm going to leave this one here. I hope you've enjoyed this one, and as usual, if you have any sort of questions, suggestions, feedback, leave them in the comments below. It's highly appreciated, and I hope to see you in the next one. All right, bye for now.